Good morning. I think we will continue with the lecture on first chapter, that is atomic bond and crystal structure. We have talked so far about different types of bonds which are there in material, and amongst them we looked at metallic bond a little more in detail. Metallic bond, as has been told, it has free electrons which are shared by all atoms, and that is why it has certain specific properties, and we also looked at how are these properties affected, say for example, by temperature or impurities. Later on in the last class, we talked about the periodic arrangement of atoms in solids. We talked about crystal structures, types of crystals which are there. We talked about 7 types of crystals, and among them in metal this crystal structure is much simpler. We talked about 3 important crystal structures that we get in metals. In short, I think so far we talked about these points, and I also gave you few examples and few problems to be solved, and I hope you have done that, because as we proceed further this will be quite important for you to understand the concepts that we are going to develop. Now, just to repeat here the 3 types of metallic crystals that are available in metal. Primarily, one is a body centered cubic. So, the position of atoms which are shown here, and normally you get this type of structure in few common metals which are listed here. Iron, I named it as alpha iron, that is the form of iron which we normally get at room temperature. Then chromium, tungsten, molybdenum. The face centered cubic structure you get in gamma iron, aluminum, copper and nickel, and this gamma iron does not exist at room temperature. You get this at higher temperature, and here you have atoms at the corner of the cube and each of the face center. And hexagonal close pack structure you get in metals like zinc, magnesium, alpha titanium. This is the room temperature form of titanium, and zirconium, and several others. This list definitely is no means by complete, and here the atoms are arranged like this in a hexagonal pattern as shown over here, and you have a set of atom down below, and also you have an intermediate layer, and here you should carefully note that position of this intermediate layer, it is just above the centroid of these 3 basal plane. Similarly, the next one is just above these 3, and the third one is just above this 3. It will be worthwhile to look at this atomic packing in little more detail. When we, let us say, suppose we try to find out what is the packing density, because as you can see here, if we assume these atoms to be made up of hard ball, and these hard ball in case of a BCC structure, they touch each other along the diagonal of the cube. And with this assumption that they are made up of hard ball, we can make few calculations. Some of these calculations, like what is the gap between interstitial that means between two nearest atom, it is not fully packed. First, let us try and find out what is the packing density, and we will see that most of this lattice, a substantial amount of space lies vacant. And what is the size of this vacant space, and where are these vacant space located, because this will be the key to the development of materials where you mix up two elements to get different types of properties. We will look at some of these calculations, and let us first try to do it for BCC structure, and which is listed here. Say, how do you define packing density? You define the packing density as the volume which is occupied by atom, assuming them to be made up of hard sphere, over the unit cell volume. So, like here in BCC, the distance between the two atoms, center of this and center of this, is equal to A. And let us assume that R is the radius of this atom. Then it is possible to find out a relationship between R and the lattice parameter, because the atoms touch each other along the diagonal directions. So, in the diagonal directions from this point to the other corner at the back, you have part of this atom, whole of this, and a part of the other atom. So, therefore, what you have, this diagonal is actually equal to 2r and 2r, that is 4r. 4r is equal to the diagonal. So, diagonal is equal to root 3 A. So, therefore, R is equal to root 3 over 4 times A. So, this is the relationship between the radius of the atom and the lattice parameter. Then we can calculate what is the volume which is occupied. Volume occupied is the volume of one sphere, this is 4 pi by 3 over r cube, this is the volume, and as I have shown last time that in a BCC lattice, number of atom per unit cell is equal to 2. So, therefore, in each unit cell you have 2 atoms. So, total volume occupied is twice this over the volume of the unit cell. You solve it and you get in this relationship, substitute this over here, then you get what is the part of, say, suppose this you raise to the power cube, and then you try and find out, substitute it here and find out what is the value of the packing density. If you go through this calculation, you will find that packing density for BCC is 0.68. So, which means a substantial part, about 32 volume percent of the lattice is vacant, and depending on the dimension of a second atom, I mean it has a capacity to accommodate very small second atom in these interstitial spaces. So, if the crystal structure changes, the nature of these interstitial and the nature of the packing density will change, and you can try and find out the packing density in case of face centered cubic and hexagonal close pack structure. And in the last class, we talked about some layer types of arrangement, if you try and recollect, you may find out there is a similarity between face centered cubic and hexagonal close packed structure. So, therefore, possibly when you find out this, you will find this is same for both, but please go through this calculation yourself. Now, having looked at that packing density, let us try and find out the relationship between the density of a particular, say suppose density of iron, is it related to its lattice parameter. If you want to find out density of any material, what you do, you find out its mass and volume, and the ratio is the density. Now, assuming that one unit cell is made up of specified number of hard sphere and they are arranged in a definite crystallographic pattern. For example, let us consider in this case a face centered cubic structure, which is shown here, where you have atoms at the corner of the cube and also you have atoms at the center of each of the 6 faces. So, in this case we know, we have calculated last time that in an unit cell you have 4 atoms in a unit cell, and mass of a particular atom can be calculated if you know its atomic weight and Avogadro number. So, atomic weight over Avogadro number will give you mass of one atom. So, in this particular case, since there are 4 atoms, mass will be 4 times A over N. Divide this by the volume of the unit cell. And if repeat this calculation for say several elements, like which has face centered cubic structure, which is listed here, say aluminum, nickel, copper, platinum, lead. Now, each of these cases you go through this calculation and the results which are shown here. For aluminum, its atomic weight is 27 and the density you find by this, you find there is an value is 2.7 and experimentally determined density is written here. There is a fair degree of correlation between the two. Similarly, for nickel also, if you do the same calculation, the theoretically calculated density matches very well with the experimental result. But you go down here, you find here that there is a large difference. Also, you see this, as the atomic weight increases down this, atomic weight increases, this density goes on increasing, but suddenly here in this case it decreases. Now, why is it so? Try and find out, and one of the things that you can do, you can question the assumptions that we made. We made an assumption that these atoms, they are hard sphere, their dimension cannot change. Second, when you are doing the packing, means by extent doing the packing, its dimension does not change. And secondly, we also make an assumption that all the sites are occupied by atom. So, some of these assumptions you try and find out, and you will get an answer why in case of lead there is such a large difference. Now, quickly I think we will look at the atomic arrangement in a particular plane, and this I am repeating it, this was shown last time. And when you arrange these hard ball like this, you automatically get an hexagonal pattern. And I said that here in the plane you have each atom has 6 nearest neighbor, and next layer of atom if you can put, which will also have exactly same arrangement. Now, they can occupy only these valleys. Now, if you put an atom here of the same size, it actually blocks part of this site. So, either the next layer can occupy this or that, which is shown here. So, this has occupied, say, first one we call it A, second one has occupied the B side, and then what happens when you bring in the third it can go to either A site or another site which has been blocked by this atom. So, in this particular case we call this site as C. Now, in a face centered cubic structure, if you look in detail, see this is if you join this, these are the 4 corner atoms of the cube, and this is the face center atom if you look from this side. In case of hexagonal structure, what you have, the third layer, the C does not exist. So, the third layer is again A. So, in hexagonal closed pack structure, arrangement is A B like that. And it will be interesting to look at atomic packing in hexagonal closed pack structure using this hard sphere model. And here let us see, suppose you have one layer of atom, on that you put another closed packed layer. So, obviously, the distance between the two layers will have a direct relationship with the atomic diameter. Therefore, hexagonal closed packed arrangement will put a restriction on these two dimensions. So, dimensions along in the plane between two atoms and the dimension between this layer and the top layer, and which it will be worthwhile to look at what is the magnitude of this. Now, here you have, this is the layer A. Now, let us see, this is the layer B. Now, if you join this center of each of these spheres, what you get is a regular tetrahedron, and this side is A. So, this side is also A, this is A, this also is A, Q S is also A. Now, what is the distance between this atom on the second layer and the base plane, and how can you find this out? For this, what you can do, you can drop a perpendicular from this vertex to the base plane, join this to the midpoint of this, because midpoint is here, and join this. So, in that case, this becomes SUT becomes a right angle triangle, and mind you, this angle is the right angle, angle U, and which is shown over here. Now, here this distance, what is this distance? Now, we say that hexagonal closed pack, we say that hexagonal structure, that C axis is different from A, parameter A. This is A, and hexagonal closed pack structure, this height of this unit cell is called C. So, this SU, so this represents distance between this plane to this central plane. So, therefore, this is C over 2. And then if you can simply go through the steps of calculation, it will be possible to show that there is a basic relationship because C is not independent, because the magnitude of C is determined by the diameter of the atom. So, it is not independent of A, and this relationship, I mean, if you go through the steps of calculation, you will find out that ratio C over A equal to 1.633. The steps are shown here, but I think you try it yourself. But so, what does this number represent? This number represents C by A ratio in an ideal hexagonal closed packed structure. If you look at the lattice parameter of the sum of the elements which I said has hexagonal closed packed structure like zinc, magnesium, titanium, you may find some of these they have a particular C by A ratio, but none of them are exactly satisfy this. Possibly the nearest that comes is magnesium, but you look up the table and see it for yourself. Now, let us look at these crystal structures a little more carefully and look at the interstitial sites that are present in a lattice which can accommodate a second element or second atom. And this will be quite of great importance in subsequent lecture, particularly to understand structure of that you get in steel. As I said, steel is an alloy of iron carbon. So, that carbon atom goes into the lattice and dimension of the carbon atom is so small in comparison to iron atom that it can be accommodated at the interstitial sites. So, when a carbon dissolves in iron, where does it go? And to understand that, let us look at the interstitial sites which are there in a body centered cubic structure. Now, here this diagram, it shows the position of iron atom, let us say, and this filled in small circles, they represent the one kind of interstitial sites. Now, we will this type of interstitial site is known as octahedral site, and if you look at this coordinates, say look at this atom and what is the coordinate. Now, in this case this axis A, B, C, they are orthogonal because this is a structure we are talking about is body centered cubic. So, cubic, that means the axis A, B, C, they are all at right angle, and you can find out the coordinates of each of these points. Say particularly this particular point is half, half, 0. We also have, so each of these face centered, you can say that these are half, half, 0. And how many faces are there? A cube contains 6 faces. Now, one of each of these face centered point will be shared by another neighboring unit cell. So, the contribution of this 6 is 6 times half. In addition, we also have sites at these points, although in this particular case, this if you look at this coordinate, it will say half, 0, 0, half. This is the midway in the C axis. Similarly, you have each of these edges one particular point. Now, there are 12 edges in the cube and each edge is common to 4 adjacent unit cell. So, apart from this there is 3 other neighbor. So, this contribution of this is 12 times 1 over 3. So, therefore, this comes out to be, this is 3 I think you check up this calculation. I think you will do it little more carefully and find out how many number of such sites are there in a lattice. Now, there is another alternative location which can accommodate an atom, interstitial atom, which is shown over here. Say this one. So, look at this atom, which is the location is A half, along B it is 1/4, 0. This site is called tetrahedral site. Now, tetrahedral site, why it is called tetrahedral site? Look at this. If you join this, this and this, so you get a tetrahedron. In this tetrahedron, this 2 are separated by a distance a, whereas these are separated by a distance which is half of this diagonal, that is, this is √3 a by 2. So, some of these edges of this tetrahedron have dimension a and some have dimension √3 a by 2. And you have each of these faces, you have 4 such sites. So, a cube has 6 faces, a cube has 6 faces. So, with 6 face, each of these 6 face you have 4 points, but each face is shared by half. So, therefore, this comes out to be 12. So, you have 12 tetrahedral sites in a lattice, whereas atom, number of iron atom in this lattice or number of atom in a BCC lattice is 2. So, number of interstitial sites per unit cell is much more. Now, if you look at this diagram a little more carefully, the other site where you have this interstitial site is present at the center of the face and the center of the edges. If you join these atoms with this, similarly one at the center of the cube, you get an octahedron. So, this site is therefore known as, each of these sites, they are known as octahedral sites. So, octahedral, it is surrounded by identical, say identical similar faces, 8 faces. This. So, these faces, they not necessarily, see this dimension between, this is A whereas this dimension is root 3 by 2. This is half of the diagonal, and which is this diagram is shown over here. So, it will be worthwhile for you to try and calculate what is the dimension of these interstitial sites and try and find out what is the dimension along this and along this. Is it same in all directions? The dimension along the face diagonal and the dimension of the gap along the edge. Try and find out what are their values, are they same? And similar thing you can repeat for tetrahedral site as well. Now, with this we have now a fairly good idea about the crystal structures of simple metals and how the atoms are arranged and what are there any gaps, where can very small atoms can be accommodated. Now, let us look at how different directions and planes in a crystal are represented. Here we use a system called Miller indices. We use this to represent directions in the lattice, direction in the crystal as well as planes of a crystal. Now, direction is rather simple, which is shown here in this diagram, and you use basically the crystal axis as the reference. A, B, C, these are the crystal axis. Now, here intentionally I have shown one plane, that is the base plane passing through A, B, and the grid lines are drawn, and to represent a direction, say for example, this direction, how will you represent? You move 2 steps, 2 units, let us say along A direction, 2 units along B direction. So, therefore, you represent this direction by these indices 1, 1, 0, although it is 2, 2, 0 and 2 is common. So, you can say that this direction is 1, 1, 0. Similarly, in this case you go 2 step along A, 1 along B, therefore, this is 2, 1, 0. What happens if it goes in the negative direction, like in this case? Here you go along A, the positive direction of A, 1 unit, and then you go another unit in the negative direction of B. So, in this case you will write this is 1, but negative along B, and it is customary to represent the site as a bar 1, 1 bar, 0. Similarly, you try and find out what will be the indices of this particular directions. But in a crystal, you will have arrangements in 3 dimension, which is shown in the next figure. Here you take one particular case, say what is this particular direction. We have joined this point with this point. So, you calculate, find out, you go 1, 2 step along A. So, you in the positive direction, then 1 step along B in the negative direction to 1 bar and 1 along C directions. So, this is called 2 1 bar 1. in certain cases the direction, maybe you are interested to know what is the indices of this. In that case, it is not passing through the origin. What one has to do is draw a line parallel to this passing through the origin, which is shown here. And now you find this is, you go one direction here, unit direction along A, unit direction along B. So, you call this 1 1 0. You try to find out the indices of particular, so this direction. Now, let us look at the indices of a plane. Now, in the case of a plane, when you look at this, this is say one crystal, and say these are the axes A, B, C. Now, suppose we want to represent, find out what is the indices of this plane. How will you represent this plane? So, this intersects, we look at that where does it intersect these three crystallographic axes. Now, this intersects at a point which is m times A. Now, m is any magnitude, I mean not it can be less than 1, it can be more than 1. So, if it is not necessarily an integer, it is m times A. Here intercept is n times B, and C the intercept is P C. So, look at, write down these indices, these intercepts. Now, what we do, we normalize it with respect to the lattice parameters A, B, C, and in that case, and then what we do, we took, so in that case it will be m n p. Now, take the reciprocal of that 1 over m, 1 over n, 1 over p, and think about a multiplier m. Now, you choose this multiplier in such a way that this reduces to integer number h k l. So, h k l are integer, and this is called the Miller indices of this particular plane. And in a crystal, you may have similar types, a set of similar planes. When you have a set of similar plane, you call it, you represent it as h k l. Suppose in a cubic structure, what do you mean by the similar plane? Say, suppose in a cube structure, you look at a cube plane which you will represent as 1 0 0. You can also have another cube plane 0 1 0. So, they are all similar. So, we say that cube plane will be represented by 1 0 0, and this will be clear, and that is possibly in this next one. Look at this crystal and let us try and find out the Miller indices of this face, which intersects only the x axis at a point m a. Now, write down these numbers m n p. Since it is parallel to B, it intersects B at an infinite distance. So, n is infinite. Similarly, it intersects C at an infinity. So, P is infinity. So, reciprocal of that is this. So, this is 1 0 0. Now, in this case, this is not a cubic crystal. So, here 1 0 0 and this particular plane is not the same as this plane. So, we say that this indices, Miller indices, is 1 0 0. Similarly, this intersects only B. So, we say that this is 0 1 0. This plane intersects only C. This is 0 0 1. Now, let us look at this particular crystal and try and index this. We say that this axis is A, this unit is A, this is B lattice parameter, this is C. Now, it is intersecting at these corner of these unit cell at A, B, C. So, in this case therefore, the index will be 1, 1, 1. Whereas, in this case this particular plane, it intersects axis A at unit distance, it axis B at unit distance, and it is parallel to C, it intersects C at infinity. So, in this case this index will be 1, 1, 0. Whereas, if we look at this direction 1, this will be 1, 1, 1 direction, and as per convention we represent dimensions a direction with this box bracket, whereas the planes with the first bracket. And in a cubic or orthogonal crystal, say particularly in cubic crystal, this direction will be perpendicular to this plane. So, this will be normal to this plane. Now, these planes can intersect in the negative direction as well. For example, here we have put this origin over here at the center. Look at this plane, here it intersects C at, let us say, unit distance, A at unit distance, and B at -1. So, in this case this will be indices of this plane is 1, 1 bar, 1. Now, this 1, 1, 1 plane in a face centered cubic structure is of considerable importance. Look at the atomic arrangement in plane 1, 1, 1 and try to correlate it with the diagram which I showed, where the hard balls, they are arranged in a plane and you bring another plane sliding over it. So, what is the indices of that closed packed plane? In fact, you will find the closed packed plane will come out to be 1, 1, 1. Try and find out how many 1, 1, 1 planes are there. And you try and find out indices of this plane. In this case, this is 1, 1, 0, and try and find out how many such planes are there in a cube. How do you represent, say suppose this indices of a plane is given, say this is 1, 1, 2 bar. So, how will you represent this here? So, it intersects A axis at 1, B at 1. So, let us say it intersects A at 1, B at 1, C. So, it is 2 bar. So, half along C. So, this is A, B and C is somewhere along the C axis negative direction. So, this is this. In the same way, you try to locate this plane 1, 2 bar, 3. Look at the closed packed planes and direction in FCC and try and find out each of these or locate each of these 1, 1, 1 plane and each of these directions, how they are arranged. Repeat the same thing in case of a body centered cubic structure. Try to locate all planes of type 110 and all directions of type 111. Representation in hexagonal, it is little more complex, and particularly this one, but directions, but it is shown over here. In case of a hexagonal lattice, this is the direction A, this is B, this is C. Now, suppose you want to find out the indices of a prism plane. So, you look at one of the prism plane is like this. It intersects only axis A over here, and it is parallel to both C and B. So, following the rule that we just saw, it is 1 0 0. But look at another prism plane, say suppose this, they are identical crystal plane. It intersects A at 1, B at -1. So, it indexes this, but looking at the indices, although they are same, they look different in the indices. So, therefore, people try to represent this by adding another crystal directions. So, this we call, but another axis like this, but this axis it is redundant, and usually this relationship will be follow. We call this axis I, and this index I will be sum of h plus k with a negative sign. So, essentially h k plus L is 1, I is 1. In that case, they become similar. All prism planes will have a similar indices. So, it will be, this will be 1 1 bar 0, it will be 1 1 bar 0 0. So, we will look at it little later. It needs a little complicated. Here the conversion is not as simple in case of a direction as in case of plane. Now, with this we now have some idea about the crystal structures in common metallic materials, and we also looked at the atomic arrangement along different planes and how these layers are arranged. But to solve crystallographic problem, like engineers, we need to develop a concept where we can represent different crystal directions in a two-dimensional figure or in a two-dimensional plane. An engineer often, to represent a 3D object, we make use of projections. We look at any solid, maybe from the top, if you look at, you get a top view or plan. If you look at from the front, you get elevation. If you look at from the side, you get the side view. Now, here when you represent a large object, three-dimensional object in this type of 2D diagram, what you do? You draw a scale down model and you give these three views to represent the particular object. And here you follow certain rule that the distance between 2 points are exactly same. You scale it down, but all these distances, they are proportional. So, these engineering projections, the distance relationship between distance are maintained. Now, in crystallography, often it is more important to know the angles between different crystallographic directions. So, here you need a different kind of projection, and we call this projection stereographic projection, which is shown over here. What you do? You imagine that you have a small crystal. Crystal is so small that it occupies the center of this reference sphere. It occupies the center of this reference sphere. What does it mean? It means that any plane that you draw in the crystal will pass through the origin. Say, suppose if you draw one plane, it passes through the origin. You draw the vertical plane, this also will pass through the origin. So, this sphere, we call this large sphere a reference sphere. Its radius is much larger than the crystal. And now, what you do is you look at a particular plane in the crystal. This plane, as I said, you will pass through the origin, and now draw a line which is perpendicular to this plane and extend it to intersect this reference sphere. Let us say it intersects this at point P. Now, you put a light source here. Look at this point from this particular point. So, maybe you put a light source here and put either a projection plane here or put a projection plane here. Imagine that. So, suppose you take a projection on this, what you do? You join this with this, it will intersect this point at P. So, this particular plane is called the projection plane, and which is shown over here. This is the projection plane, and this point is shown here. This point is called pole, whereas this particular plane will intersect this reference sphere at certain points. So, which is shown here. It intersects somewhere here and here. So, these intersection points will come here like this, and this particular plane will get projected like this. And in this case, we call this point P is a stereographic projection. This P is a stereographic projection of this pole P. And this particular type of projection, what is retained is the angular relationship, and these angular relationships are maintained. So, that is why we call this as an angle through projection, and you are very familiar with globes. If you look at the globe, you have the geographical globe. If you look at, you have certain great circles which are drawn. So, equatorial plane, so another plane, vertical plane which goes through the center of the globe is like this. We call all these great circles wherever the diameter of the great circle is equal to the diameter of the reference sphere. And we also have a set of line in the globe which goes like this. We call these latitudes. So, here also you can think about a similar situation and look at a projection of this kind of a ruled globe, which we call Wolf net. And Wolf net, a typical figure is like this. Here all these are the great circles, and these have diameter which is equal to the diameter of the reference sphere, and you can clearly see that distance relationship is not maintained, but angular relationship will be maintained, and you will have this kind of projections of these small spheres, small circles like this, they are called latitude. It is exactly similar to that globe, and this type of reference net one uses, it is called Wolf net, and this is used to measure to perform angular measurement on stereographic projections. So, in this class I just introduced you the concept of stereographic projection at the end. This concept is a little abstract, and maybe we will next class we will talk about it in a little detail. And apart from that, we also looked at the atomic arrangement in different crystals which you find in metals little critically, and given you some of these exercises. I hope you will try to solve them. Thank you.